All right. Okay, before I begin, I realized that for my first and fourth period, I didn't catch a mistake before then. I'll work through each problem, but I just want to let you know that I made a mistake for number 2. I forgot to distribute that 4x to the -1, and I made that a positive 4x, and then that threw off. So if you were working through yesterday and try to figure out why your sign may be different than mine, that should be a plus there. So I'll go through everything. Just wanted to point that out in case you did not. Yeah, I didn't get a chance to tell you yesterday. Okay, so number 1, it's going to be all power rule that will get us to where we need to go. So we just have to expand all the way out. We could do product and chain rule, but it's not worth the effort here. Let's just expand everything out and rely on power rule. So I see the x-1 squared. I'm just going to just pull that out for a moment. No, it's not. It's not. But I just want to point out that students could do chain rule, but we don't want to. It's just easier to just fold everything out. Okay, so I want to make sure that we flow this out correctly. X squared minus 2x plus 1, distribute the 7x cubed through. So I'm going to see if I can get every term set up and ready for power rule. Distribute the 7x cubed through. I get 7x to the 5th. Okay, we keep going. This is basically ready for power rule, but we like to push coefficients in front of the variable and so that it doesn't look like it's beneath it. E is just a number like pi, so we know that's not a variable. We know that's just a constant, right? Okay, so this is where we want to be before we even begin our calculus step, right? Everything is nicely set up, ready for power rule. All the parentheses have been resolved. All the expansion has been resolved. All the radical in the denominator has been moved up. All the radical has been converted. Any numeric value that's below a variable has been pushed out in front. So I think that's the hardest step for a problem like this, just to be able to know how to get it ready for power rule. Okay. The 3 doesn't move up, it stays below, only the x moves. X is 7/2. Okay, and when we bring that up, it's x to the -7/2. Okay, everybody okay with that first step? Okay, so now we can do power rule. Okay, so we go through the same steps for every term, bring the exponent down, subtract 1 from the exponent, except for this, we know that's a constant, that's just going to go to a 0. Okay. Once we bring that 4/5 down, we subtract 1 from the exponent. 4/5 minus 5/5 is -1/5. 2/3 times -7/2. And then we're subtracting 1 from the exponent. -2/2 is -9/2. I pointed out this the other day where sometimes students feel like they want to move towards 0, so they start adding 1 to the exponent. So just keep in mind that for power rule, you're always subtracting 1. So if it's a positive value, it will get closer towards 0. But if it's a negative value, it's going to get more negative. Okay. So this cleans up to be -7/3 here. We're basically at the answer. The only cleanup here is try to get those x back down to the denominator, since your last point there is just to, can you present your answer with no negative exponents? Oops, sorry. Okay, how do we feel about power rule? Everybody okay? All right. Okay. Number two. Number two is also power rule, even though it looks like it could be quotient rule. There's only one term in the denominator, so if we just split everything up, clean everything up, we're ready for just relying on power rule. So we're going to expand out, distribute, clean up the numerator and denominator separately, and then we're going to split up into individual fractions, and then clean each fraction up, and then go through power rule. Okay, so I'm going to put this here, 4x. This is really x to the 1/2 plus 3x minus 1. Okay, I'll distribute that 4x through. When I distribute the x through, I'm adding exponents. 1 plus 1/2 is 3/2. From here, we want to go ahead and split up into individual fractions. I want to make sure that we understand that we're not ready for power rule. Okay, I see some students, I've done this in the past. I want to make sure that no one does this on the quiz. They would take this and they would say, well, I'll do power rule here, power rule here, power rule here, power rule here, and then that's my answer. So that we can't, when things are stuck like this, power rule is not going to be effective. Okay, so we can't do this. Okay, that is not correct, right? It feels easier, but with power rule, we have to follow our restrictions there and our conditions there. Okay, so we can't quite do that. Okay, but what we can do is we're still in the cleanup stage. We're still not ready for power rule until every term is separated from each other. So we're going to do this here. So we're still in the cleanup stage. So the nice thing about splitting up into individual fractions is that you realize, okay, this is really 3 separate terms. These are independent of each other, but we're still not quite ready for power rule because we have variable in the denominator. So we have to bring it up. Easy way to bring it up is just subtract exponents. I mean, you can bring it up as x to the -9/2 and then add exponents, but that's the same thing. Right? Negative to the top and adding the same thing is just subtracting the exponent as we see above each other. Okay, so I'll go ahead and do that, but we're still under y equals. We haven't done anything calculus yet. 3/2 minus 9/2 is going to be -6/2. Two minus 9/2. That's the same thing as 4/2 minus 9/2. 4 over 2 minus 9 over 2 is negative 5 over 2. This is 1 minus 9 over 2. That's 2 over 2 minus 9 over 2. That's negative 7 over 2. Okay, any questions so far? So this is where we want to be before we do power rule, okay? But you see how every term is nice and clean, right? Everything is ready. We can just go through power rule, okay? And then from here, or after that one step, we're pretty much at the end. Okay. Another issue I see students experience is that, you know, there's a lot of algebraic steps that leads to this point. And, you know, the subtracting of the exponents, the moving, the cleaning up, students feel like they've already gotten to the derivative, so they leave this as their final answer. Okay, so we haven't done anything calculus related yet. We've cleaned it up, but we haven't found the derivative yet. Okay, so we still have to do our calculus step. Okay, so now dy dx. Okay. Bring the exponent down in front. That's really -3. If you want to make that -3, you can, but I'll leave it as 4. So -3 minus 1 is -4. -5 over 2 minus 2 over 2. -7 over 2 minus 2 over 2 is -9 over 2. Okay, and I just want to assure you that, I mean, if you make a mistake here, it's not all or nothing. Okay, I'm looking at your steps. If you somehow miss a negative here, or you made a mistake here, I'm still looking at all your steps. I'm giving partial credit. It's not like, oh, you miss a negative here, you missed the whole problem. I'm looking at your steps. If I see that you understand your steps, but you made a mistake here or there, I'm still giving the majority of your points. Okay. I care more about your process than, you know, little mistakes that you're making. Okay, so this ends up being -24 over 10, which I can reduce it forward 2 there. I can make it -12 over 5. The 5s can cancel out. 12 over 2 can cancel out. I get 6x to the -7/2. And then here, when I bring that negative down, there's 2 negatives there, so that's going to become positive. I can make that a 2 here, so 14 over 5. Okay, so we basically have the derivative. We can just, I'm still doing some minor cleanup here. You see there's all these negative exponents. Let's push them back down to the denominator there. Okay. Okay, number 3. Our function is x over x squared minus 2. Find f prime. So here we see a denominator relationship, but there's 2 terms in the denominator. We're forced into quotient rule, right? It's not the same as this, where we can avoid quotient rule by splitting up into individual fraction. There's only 1 term here, but there's multiple terms below. Even though this looks simpler, we can't avoid quotient rule here. Okay, we got to go through quotient rule. Okay, so let's find f prime. Let me write f of x again. So my numerator is my f, my denominator is my g. Go through quotient rule. Okay, f prime g minus f g prime. Common mistake that students make with quotient rule is they do the numerator, but they forget about the denominator. So the denominator, the g squared, is also part of your derivative rule. All right, so f prime is derivative of x. X's derivative is 1. G, no changes. Back to f, no changes. And g prime is asking for the derivative of the denominator. X squared minus 2 becomes 2x. All over my denominator squared. Okay. Now, once you have your derivative in quotient, after going through quotient rule, make sure that you avoid a couple mistakes. One mistake is trying to do something with the denominator. Leave the denominator alone. It is complete. It's only the numerator that requires more work. Okay, so do not try to cancel out. Do not try to FOIL out the denominator. Just work on your numerator. Okay. Okay, so the 1 distributes, which doesn't change anything. Minus x times 2x, that's net minus 2x squared. Okay, so we haven't found the answer yet, but we have all the tools that we need to get to everything that we're looking for. Okay. Any questions so far? So we're asked to find the equation of tangent line. That means there's a couple things we need to gather. We need to gather the order pair. We need to gather the slope, and then point slope form. We don't have the full order pair or the slope, but we do have something that we can start using. We have x equals 1, so to find the order pair, we can involve the original function. So we'll plug 1 into the original function. That'll give us our y value. Then we'll plug 1 into the derivative. That will get us our slope. And once we have our order pair and our slope, point slope form. Okay, back into the original equation here. So it's 1 over 1 squared minus 2. Okay, f prime of 1. The slope at 1. I'll insert 1 in for x. Okay, everybody good with finding order pair, finding slope, knowing where to, which function or what the function derivative, what they get back in return and how to interpret it. Okay, so once you have your order pair and your slope, point slope form, that's your equation. Okay, everybody comfortable with the first page? Yeah. Which number? Number 2. I already went over number 2, so let me go through the rest of the worksheet and then I'll go over it with you on one-on-one. Any questions with 3? All right, let's go to page 2. Okay, particle moves along the x-axis. X of t is given by the equation that you see there. Meters per minute. So make a note of that. Your units here. Include units with your answer, find velocity and acceleration. So we'll go ahead and just build our derivative. This is nice and easy here, much easier power rule than on the first page. We can jump directly into it. All right, so we go through a power rule again to get from velocity to acceleration. Yeah, yeah, on the quiz, I'm going to give you.
So we just
position. That's right. That's right. But if I were to give you velocity, then I could only ask you about velocity and acceleration. I wouldn't be able to ask you about position if I started with velocity. Okay. So if I gave you velocity, that means you're already sitting. That means you're already here, and you can go from here to here. Okay, what is velocity in 1 second? Pretty straightforward. Acceleration in 2 seconds. We can just insert our t values into the respective functions. Okay, 3 minus 12 is negative 10 minus 15, negative 9 minus 15, negative 24. Okay, what's our unit of measure though? Meters per minute. Yeah, make sure that you're not just assuming what the units of measure are, that you're looking at what the problem gives you and you use the appropriate units for that problem. Okay, acceleration to 2 seconds, insert 2 in for t. Ends up being 0, but what's our unit of measure there? Yeah, meters per minute squared. I see some students do meters squared per minute. That's something different. Meters per minute squared. Find the average velocity of the particle on the interval from 1 to 2. Okay, what's the formula for average velocity? Change in position over change in time. I mean, I understand why students struggle with this. You see velocity, but you want to involve position, but you have to involve position. I was just thinking of, what is something that is I can connect with you guys where we can make it easier to see that relationship. Well, how about think about this, right? If you think about velocity and something that is tangible for us for velocity is when you're driving, right? When you're driving, miles per hour, right? Miles per hour, that's something that we know what it means, 45 miles per hour, 60 miles per hour. If you think about what this is miles per hour, right? That's velocity. And if you look at your units here, miles, that is a position unit. Hour, that's a time unit. So it makes sense, right? Miles per hour, you have change in, that's a position unit over a time unit, right? So maybe that helps. I see some students, they want to do change in velocity over change in time, or they want to do change in acceleration over change in time. So if you can connect velocity with miles per hour, maybe this will help remind you what units, what you want to use to get to your velocity. Okay. Right, so we're going to insert 1 into the position function. So that's 1 minus 6, that's negative 5. Negative 5 minus 15 is negative 20. Negative 20 plus 1 is negative 19. Yeah, sorry about these numbers ending up a little bit large here. It'll be, I think, a little bit more manageable on the quiz. So if I plug 2 in, I get 2 cubed is 8. 8 minus 24 is negative 16. Negative 16 minus 30. Negative 44 minus 1. Sorry, negative 46 plus 1, negative 45. Yeah, it'd be easier to work with because you won't have a calculator here. But even if you make a mistake, I'm looking at the work, and if I see that you understand what you're trying, if I see that you understand what I want you to do, then I may even give you full credit, just because I care more about that you understand the process rather than more so than you made a silly mistake with adding and subtracting. Okay, so negative 45 minus negative 19 over 2 minus 1. Okay, so negative 45 plus 19, negative 26 over 1. That's negative 26. Okay, what's our unit of measure here? Okay, part E. When is a particle at rest? What's our strategy there? At rest, what does that mean? Okay, velocity is 0. Okay, so we take our velocity function, we replace v of t with 0. Here's my velocity function. I'm going to find the time when the velocity is 0 and factor out that 3 here. Oh, sorry, minus 14. Multiplies to be negative 5, adds up to be negative 4. The 3 is not going to produce any t values for me. It's only the t minus 5 and t plus 1. So t minus 5 equal to 0, I get t equals 5. T plus 1 equals 0, I get t equals negative 1. I set each parentheses equal to 0. So t minus 5 equal to 0 and t plus 1 equal to 0. And I just solve for t. So these t values, they could both work, but it depends on the domain, right? If it says, use time for all real numbers, then we want to keep both these values. But is there a restriction on time? T is greater than or equal to 0. So we obviously have a value that is outside that interval, that domain. So we take negative 1 out, only 5 we keep. And what's the unit of measure for 5? Oops, I made a mistake here. 5 what? 5 minutes. Yeah. My key said 5 seconds. Exactly, right. Less than 0, right? Okay, part F, find the average acceleration of the particle from 1 to 3. So let's look at average velocity and look at how we define average velocity. We can kind of take that and adapt it for average acceleration. What do you think the definition for average acceleration is? change in velocity over the change in time. Okay, so we don't touch the acceleration function. We look at the function above it, just like average velocity. Average velocity, we don't touch velocity. We look at the function above it. Okay, so insert 1 into the velocity function, v of 1. We found that from part B already, negative 24. V of 3 also ends up being negative 24. So average velocity, average acceleration ends up being 0. Okay, that's not always going to be the case. Okay, we don't want to just always assume that it's always going to be 0. Make sure you go through your work and arrive at your answer based off of what we gathered here. But what's our unit of measure though? Meters per minute squared.
Is it only squared when it's acceleration?
That's right. The reason why is because velocity is meters per minute, and then time is minute. And when we merge those together, it ends up being meters per minute squared. Okay, when is a particle moving right? When does a particle change direction? We have to rely on our velocity sign line, velocity number line. So we have everything that we need to build our velocity number line. We have a location where the object is motionless, and we have a domain restriction. So we'll put 0 and 5 onto our velocity number line. Because we know that on the number line here, 0 is a starting point for us because t is greater than or equal to 0. So we know there's never going to be any t values greater than 0. And then velocity is talking about movement, right? So we want to basically have our intervals of movement separated by places where the object is not moving. So we're always going to place velocity, whatever velocity 0, we're always going to use that to help us separate our intervals. Well, it depends on whatever you get here. We only want to put time values where the particle is at rest on the velocity sign line. The 0 came from the fact that that's part of our domain restriction. We know we can't get negative numbers, so that is a endpoint for us. No, there's not.
So any domain restriction will be like the first number.
Yes, that's right. Yeah, if it said particles moving for all real numbers, then that means there is no starting value. That means your negative and positive numbers are involved, and you're only going to place values where where velocity is 0. Okay, so we want to go ahead and try to fill out these sign lines. We know that in each of these intervals, the object is either moving to the left or the right, but it's just going to be the same direction all throughout this interval. And then from 5 to infinity, it's also just going to move in the same direction. I'm going to pick values that I think are easy to plug in. So I'll plug in 1 and 6. These are numbers that the smallest numbers I can find closest to 0, but you can choose any number that you want on number line, as long as it's between 0 and 5, and as long as it's greater than 5. Okay, the way we test is we plug into our velocity function. I like to put it into the factored form. It's the easiest one to gather and to collect your signs. So if I insert 1 in for t, okay, 1 minus 5 is negative or positive? Negative. Negative. Okay, 1 plus 1 is positive. Negative and positive gives me negative. So I know that from between 0 and 5 seconds, this object, this particle is moving to the left. Okay, let's insert 6 in for t. 6 minus 5 is
Positive.
6 plus 1 is
Positive.
2 positives, tells me positive. So when the timer starts, the particle is going to start moving to the left for 5 seconds. It's going to stop, turn around, and move to the right, and it's going to continue moving to the right. And it's not going to stop, so keep moving to the right. Yeah, exactly. Yeah, if you do what I did here and just do it in your head and just put that there, that's good enough. It'll still be the same. You mean the original velocity function?
Yeah.
Yes, still the same. I like this one better just because there's less calculations involved. But yeah, you can do that. Sure. All right. Now I do want to point something out here is that do not use the 1 and 6 for anything else. I see some students, they try to do, intervals from 1 to 5, or they involve the 6. As soon as you get that minus and plus to show up, these have no more use for us. Okay, we're not going to touch those numbers again. For any interval that we're gathering about moving left, moving right, particle change direction, it's only involving what you see on the number line initially. It's the 0, the 5, in this case, the infinity, because infinity is to the right of my velocity sign line. Okay, so then based off of this, when is the particle moving to the right? Yeah, from time 5 minutes to infinity. And the reasoning is because velocity is greater than 0. Okay, what about when does the object change direction? At 5, because velocity changes signs. And make sure that you say, if you say it changes signs, that's not specific enough. Make sure you say velocity changes signs. Now I know this isn't that, it doesn't ask for it, but when is the particle moving left? Zero to 5, is that what you said? Because less than 0. Now, is this fully correct? What do we have to consider? 0. What about 0? Because we have to at least consider the fact that, oh, 0 is part of my number line here, and it is part of my domain. So if there's movement at 0, we need to include that as part of our interval, because we know the object is not stopping at 0, right? Only stopping at 5 and -1 doesn't show up in our velocity equal to 0. So if I insert 0 into a velocity function, let's see what's happening at 0. So if I plug 0 in for t, 0 minus 5 is negative. 0 plus 1 is positive. Negative times positive is negative. So that means when the timer starts, or right at 0, this object is already moving to the left. So we need a what at 0? Bracket. We need to include that as part of our domain. I know it's not part of the this problem, but I think it's good for us to look at that. Okay, part H, what is the displacement from 1 to 4? So displacement has a formula. Displacement is just a change in position. Okay, it's not the change in position over the change in time, it's just change in position. So basically, it's just the top portion of the average velocity function. It's just x of 4 in this case minus x of 1. We just want to figure out how far is the object from where it began. Again, sorry about these numbers, are a little bit large here. X sub 1 is negative 19. And X sub 4 is negative 91. Okay, so negative 91 minus negative 19. It's okay to have negative displacement. Okay, total distance from 3 to 6. So the first thing we got to consider is there a change in direction between 3 and 6? Because if there is, we got to do some additional work. There is, right? So we need to find the location of this particle at 3 minutes, 5 minutes, and 6 minutes. If there was not a change in direction, then it'll just be the same formula as displacement. And then make the number positive. Yeah. Okay. So x of 3 means insert 3 into the position function. X of 5 means plug 5 into the position function. X of 6 means plug 6 into the original function. But position function. But you know, these numbers are large. Sorry about that. So I'll just tell you the numbers right now. Okay, but everybody good with where and why we chose these numbers to plug into the position function? Okay, so we don't want to be adding these numbers. Okay, what you want to do is you want to imagine these are numbers on a number line, and you're walking between these locations on the number line, and then each step that you take, you're just counting the steps in your head. So let's say you have a number line here, and negative 71 is here. Negative 99 is here. Negative 89 is here. Okay, just put them in order. And you're walking from negative 71 to negative 99. And then you're turning around and you're walking from negative 99 back to negative 89. And you just imagine yourself walking and you're just counting your steps, positive steps. And at the end, you're just going to total your steps together. And that's going to be your total distance. So between negative 71 and negative 99, how many steps would you have taken? 28, because you just subtracted it, right? Negative 99 minus negative 71 is 28 steps. And then from negative 99 to negative 89, how many steps would you have taken? 10 steps. And then so how many total steps did you take throughout this process? 38. Now, I say steps just so that you can have a visual, but you want to just match whatever units it has. On the key, I messed up. I said feet, but it should be meters. So yeah, total distance is always positive. Displacement can be negative. But the issue students run into here is they want to add these numbers together. But I feel like if you can visualize yourself walking on the number line, I think it makes it easier. Doesn't feel as complicated. Okay, last two here. Is speed increasing or decreasing at t equals? Sorry, I made a mistake here. I think I told you that I meant for it to be t equals 1 because t equals 2 doesn't quite work out. So how do we determine if speed is increasing or decreasing? What do we look at? And acceleration. Good. So we want to find v of 1. We want to find a of 1. And we want to simply compare their signs. If the signs are the same, speed is increasing. If sign is different, one is positive, the other is negative, then speed is decreasing. So v of 1 is negative 24. A of 1 is negative 6. They're both showing negative. They both have the same signs. Speed is increasing here. And our reasoning is because, okay, if you just say because opposite signs, that's not enough. Okay, I want you to specify what is it that have opposite signs. You can say B of t and A of t have opposite signs at t equals 1. Or we can say V of 1 and A of 1 have opposite signs. That's fine as well. Sorry, they have same signs. Increasing same signs. Thank you. Okay, last one here. Is velocity increasing or decreasing at t equals 3? Is this talking about velocity? No. Okay, you see velocity, but it's not talking about it because the increase decrease changed it. It's talking about the rate of change of velocity. And what is the rate of change of velocity? Acceleration. Just acceleration. So what is acceleration at 3? 6. And that 6 tells us that velocity is what? Yep, so we say velocity.
Because it's positive.
Yep, velocity is increasing. And I want you to say because A of 3 is greater than 0. Or we can say A of t is greater than 0 at t equals 3. Either way.
Or, if it was negative number, then it would.
If acceleration is negative, then velocity is decreasing. Okay, I'll go back to the first page. I know some students had questions about number 2. Let me just walk through that again, and then I'll come around and see if you guys have any individual questions. So number 2 here, this is just a power rule problem. We can distribute the 4x through. But we have to do quite a few steps of cleanup because we want to separate into 3 individual fractions. And once the individual fractions are separated, we still want to make sure that we bring up all the denominator variables by subtracting the exponents. And then once we are at a place where everything is nicely set up for power rule, everything is separated, then we can just do power rule, going through our process. But on my key, I did make a mistake with this negative sign here. So if you got your answer being, yeah, so this is correct here. It should be a plus there at the end. Yes. Yeah, question. Oh, sorry.
Can we use product rule for this one?
It's not going to come out as easily, so I want you to use power rule is it's gonna allow you to get to an answer that is simplified.
What's the example of a fraction that you would use product rule for?
That's right here. Number 30. So as soon as there's 2 terms in the denominator, you're forced into. Wait, hold on. What you say?
Product
Oh,
rule.
product rule. Sorry. Product rule we can avoid right now because everything that we have is easy enough where you can avoid it by just expanding and doing.
So we probably won't have a question that's just power rule
Or you mean just product rule?
or just product.
Yeah. Any product rule right now can be avoided because
Just multiply.
because everything that I have right now is simple enough to do it. Once we get into our test, then with chain rule and everything, we are forced into product rule or implicit we're forced into product. So right now, yeah, you can avoid product rule if you want to. Yeah.
You're going down, like, do you have to do y equals or like the x dy over dx equals?
Yeah,
x
because
squared?
I want to know what, that you know where you are.
And then do you only change it to prime on the final answer, or is it never change?
As soon as you apply power rule, you can then do y prime.
Like,
Right, so from here to here, I did power rule. So once I do power rule, then I'm sitting at the derivative level. So everything after this will be a derivative.
So dy over dx is already like, that's prime.
That's y prime. That's
And I'm gonna do just y.
you can say y prime. Yeah.
Is this gonna look like our quiz?
You can do this. You should feel good. Okay, I'll come around, see if you guys have questions.
Where is this? Is that wrong? Probably different. I don't know how you got this. So you can say.
If I divide both 14 and 6 by 2.
Yeah.
Yeah. But if you didn't reduce it, I would still give you credit. But I do want the negative at 0.
Yeah. I was. Yeah, I was just so confused.
These two, I'm solving them direction.
Yes. Doesn't, then you just, then like.
I know, well, you see them like start, you see like subtracting fractions up there. I'm forgetting everything. So. He's not able to do everything.
This is easy as well.
So. X is the first power. Okay, so let's do power. Anything to 0 power is 1.
Okay, I was thinking yes.
Yeah, you made the 0 power without 0.